Thank you very much for kind introduction. Also, I have to express my sincere thanks to conference organizers who are working very hard to make this conference a great success under very difficult pandemic conditions. So I'd like to talk about fault problem today. This is an example of fault. And fault used to be a scientific topic in the previous century, but nowadays it's becoming an engineering topic. This is open pit showing fault dislocations in vertical direction, and the details are shown here, and you can easily recognize that grains moved or rotated like this due to fault movement. So you can understand that the ground along the fault plane is prone to strong deformation. So first topic is this one. I have 8 topics. And this is the history of earthquake magnitude in the world since 1950. So it's very interesting that in the 50s, 60s, and then after 2000, we had very many gigantic earthquakes with magnitude greater than 8.0 or 8.5. But in between, we used to enjoy a quiet time in 80s and 90s, in which earthquake magnitude was less than 8.3. And to me, it's important that many disaster technologies, not only geotechnical, but also structure or others, were developed in this peaceful time. And question is, those technologies and the way of thinking were still good in the 21st difficult century. Probably we need to develop a different way of thinking now. Also, rainfall is another issue, possibly because of global climate change. This is a Japanese record since 1945, showing the rainfall during disasters, flood and other rainfall-related disasters. Clearly, the upper bound is increasing. So we have more risk of heavy rainfall, and possibly rainfall disaster is combined with gigantic earthquakes from now on. So combined effect is my concern. First, we may have heavy rain and then big earthquake, or inversely, big earthquake first and then heavy rain. So combination of 2 types of disaster is of my concern. Let's see examples. 1995 Kobe earthquake with magnitude 6.9, and then 2004 Niigata Chuetsu earthquake 6.6. They have similar magnitude, but the consequence is different. Kobe had a few notable landslides. Like one of them is shown here, and this earthquake happened in January. It was the middle of dry winter in Kobe. And Niigata Chuetsu earthquake happened in October. That was the end of rainy seasons. So there are so many landslide problems, as you can see here. And this is the accumulated precipitation, rainfall, for 4 months before the earthquake. So Niigata Chuetsu had much more amount of rainfall than Kobe. So this difference created combined effects in Niigata Chuetsu. So I'd like to say that 2 events do not have to occur at the same time, same day, where actually interval of several weeks or months are still important to make combined effects. The long-term instability after big earthquakes. I was very much impressed by the aftermath situation in China after Wenchuan earthquakes. This is one of the disasters. Mountain slopes were affected by strong shaking first. And okay, this is well known. However, the mechanism by which mountain slope is affected by shaking is still not fully understood yet. But I'll address this topic later. I'm also much interested in Pakistan experience after 2005 earthquake. This slope was stable, no problem after the earthquake, but then, then something started, and this is a consequence. So this is a totally developed after the earthquake, and this is area changing with year. At the top, we have okay, earthquake happened in 2005, and black symbols indicate the landslide area. It increased in 2005 like this, then decreasing. This means stabilization. And at the top, we have vegetation area. Vegetation decreased by landslide. Then, okay, trees, forests are coming back like this. So this procedure, curing time is more than 10 years. So long-term instability continues for say 10 years or more. Taiwan had the same problem. There are lots of debris deposits in the valleys after the earthquake, and during heavy rain, many sediment disasters happened for more than 10 years. So it was a long-term disastrous situations. So I call such a situation as one of the combined effects of earthquake and heavy rainfall. And also this is a very interesting report from Taiwan. Vertical axis is the landslide area. Previously, landslide was very small in this study area. Chichi earthquake triggered so many landslides. Afterwards, every heavy rain, hurricane, typhoons cause many landslides, but okay, we have decreasing trend. This means stabilization that took 20 years or even longer. So this is a very difficult situation in Taiwan geology. Now we move to Kobe. This is an old picture in mountains in Kobe. Earthquake happened in January. So top picture was taken in April before rainy season. Then after rainy season, you can see landslide area increased. At the second place, similarly, landslide area increased from this to this one. So this also suggests that the earthquake-induced slope instability and heavy rain increase the size of the landslide. So fault is important. This rupture in Pakistan, this fault dislocation, and this fault is just heading towards the landslide. Also, I saw many landslides along the Coseismic land, along the fault lines. Pakistan. So this is a summary of the location of landslides published by this Dr. Shafiq, and you see landslides occurred are concentrated along the fault line. Example, data of China is very famous, well known. I don't have to talk too much about this, but many landslides happened along this mentioned fault. Kaikoura, New Zealand is also similar. Many landslides happened along the fault. So in the 20th century, landslide people used to talk about the importance of epicentral distance affecting the vulnerability or likelihood of landslides during earthquakes. But now we have bigger earthquakes. So now we need to have different way of thinking. Distance from the fault is more important than distance from the epicenter. This is one of the new ways of thinking. So existing faults, what does it mean? In my presentation today, existing faults means those faults that had slipped before, maybe 1,000 years ago, 2,000 years ago, but did not move during the recent earthquake. Still, those faults affect slope instability today. I pick up two existing faults today. First one is Itoi-Gawa-Shizuoka tectonic line, at which Japanese islands are distorted or rotating. So we have significant tectonic disturbance along this line. Second one is called median tectonic line. It has 70 or 80 million years history, and it has been moving this way or this way. It has a very complicated history, but disturbance occurred along this line. Ancient fault ruptures created many fissures and weak planes. This is my point. So they trigger slope failure now during recent earthquakes and heavy rains. Let's look at the example. First one is Oya landslide. It is very close to Itoi-Gawa-Shizuoka line. And I went there, I climbed this very unstable slope. It took me 2 hours from bottom to the top. And this is said to be produced during 1707 gigantic Hoei earthquake. And entire mountain is made of slate, etc. I say mountain is not a rock mountain, it's made of crushed stone pieces. Crushing occurred due to action of many nearby local faults. It's so difficult to climb this slope. I made 1 step and I slipped down 1.5 steps. So it took me 2 hours. Oya site is here, and there are many tectonic lines, faults. They moved some time before and crushed this mountain into pieces. And also, creep is going on here. I climbed up this slope and came here and walked this way. And creeping is going on in this mountain. Creep means weakness. Particularly depression is here. This is the lowest point. And this is another creeping effect. And Oya landslide repeated failures, debris flows for 3 centuries since its initiation is early 18th century. So bottom of the valley is filled with stones. And near the Oya slide, there is another one that is called Shichimenzan Mountain over here. It is close to Mount Fuji, and there is a fault here. This is part of Itoi-Gawa-Shizuoka tectonic line system. So this is the appearance. It's amazing. So some mountain climbers can walk up this slope, and I don't want to do that. I'm a very good gentleman. I don't like such that type of terrible activities. But this is the top of the cliff. The mountain is still falling down continuously. And this Shichimenzan slope is also undergoing cliff deformations behind the cliff. Now my shape is like this, so left-hand side is now going down slowly with time. Finally, this part will fall down entirely. And that old picture, 1847, there was already a landslide here. So we can see that we understand that this slope instability has been continuing for 200 years. Or some people say it started 1,000 years ago. And creep, depression made pond like this. And one more is Shiratori Mountain, south of Shichimenzan. Here, Coseismic landslide happened in 1707 during this gigantic earthquake, and still we can recognize that part of slope failure. So I went there, and the surface is covered by fragment deposit, stones. So again, I understood that the mountain was sometime before crashed into stones, and this portion of mountain is unstable. Then I move on to this second median tectonic line. I visited this portion 2 years ago. No, last year. So this is a fault line like this. And this is a cross section of the fault plane. So left-hand side, right-hand side have totally different geological age, mineral type, etc. And there are many unstable slopes. This slope fell down in 1963 during very heavy rainfall. Another one is like this. On this slope failure is continuing during every year. And this is a very new one. So this is interesting historical informations. Vertical axis shows the severeness of disaster. Maybe we can look at the three severest among the examples. And the red symbol shows earthquakes that affect this region significantly. And this area, maybe this one with scale 2, always followed by rainfall disaster. Rainfall disaster includes slope failures. So we have some correlation or earthquake effects on slope stability after the earthquake. So probably, I say probably, the mountain slopes became unstable after strong shaking, as occurred elsewhere at many places in the world. Creep is also very important, interesting. So last year I climbed this mountain. I walked along this ridge. It was a very tough walking, and I came to this place. And creep suggests future instability. What happened? I cannot see. Sorry, something wrong, but there are several causes of long-term instability of slope after big earthquakes. One is rock mass fracturing, as I saw you already. And I'll touch upon the keyword process zone later. Creeping also. And then slope damage by strong shaking and deposit of fallen soil mass in the valley bottom. There are 4 causes of long-term instabilities. So this is the mountain that is now undergoing creep deformations for 10,000 years. The rate of movement is 1 centimeter per year. I came this way. Okay. And this is a laboratory test on creep deformation. It's unconfined compression test on man-made rock specimen. So creep, long-term creep suddenly triggers collapse of samples at a stress level lower than the peak strength. So creep makes rock weaker. So this is another mechanism. Strong shaking disturbs the mountain slope, and here you can see big cracks. As you know already very well, this crack suggests the initiation of slip failure. Also, surface water can easily flows into the slope. And this is a valley deposit of fallen soil. So process zone. This idea was originally proposed by Vermilion and Schultz many years ago. And I guess the picture here, top and bottom, suggests disturbance, mechanical disturbance, damage produced by fault actions in the previous times. So fault makes some mechanical disturbance within some range of distance. This area is called process zone. So engineering concerns the size of this process zone. So the original authors suggested that length is 1% width is 1% of the fault length. Then I collected more data, landslides near existing faults, and plotted more data. And my conclusion is that the idea 1% of the fault length is not very bad. Okay, it's good enough for practice. So within 1% from the existing fault, we have to be more aware of, we have to be more careful about slope instability, failure during heavy rain. So mysterious water ejection. Water is always our enemy, although we have to drink water every day. So Matsushiro earthquake swarm in 60s Japan created so many minor tremors in 2 years or so. This water ejection during the Matsushiro earthquake swarm, sometimes water was warm, 30 degrees Celsius. The fish was killed. Also, groundwater suddenly obtained high pressure, and this type of ejection started. This is not a major topic today, but earthquake light is said to be a precursor of earthquake, and these are two scientifically trustable shots of earthquake lights. And Matsushiro swarm was actually probably triggered by water volcano effects. This is not this is different from the traditional idea of earthquake triggering. Tectonic water came up from the depths of the earth, and high water pressure reduced effective stress in local fault, and slippage happened. And also, water ejection triggered this landslide. This is an aerial view. This is the present view. Okay, near the Matsushiro, there is an area of Matsunoyama landslide, where big landslide happened suddenly in 1962. And this was probably caused by geopressure. What is geopressure? This is geopressure means high groundwater pressure triggered not by liquefaction cyclic erosion, but Earth's actions. And here we have hot springs with salty water. So salty water suggests fossil seawater. So this is geologically very special place. And this is the eruption of mud volcano. This mud volcano implies underground geopressure. By the way, it's very difficult for me to find out this small, tiny mud volcano. The diameter is only 5-10 centimeters. So I had to walk in the bush, and finally I found this mud volcano. I'm a good detector. Also, USA had similar mysterious water ejection in 1959 Hebgen Lake earthquake, 1983 Bora Peak earthquake. There are several interesting photographs in the report. Maybe this is a good topic for North American researchers and engineers. This place is far from me. And now I have a question to the conference organizer, Professor Van Lamming. In his recent publication, he referred to very mysterious water ejection prior to the Haiyan earthquake in 1923, if I remember correctly. After that, this less slope landslide happened. So I'm quite interested in the geological mechanism that triggered this water ejection near the top of the slopes. So last topic is pull apart structure. In this conference, some people are already talking about seismic landslide that happened in Sulawesi Island. And I've been also engaged in research. I'm trying to write a report nowadays. It's quite mysterious. It happened in pull apart basin like this, pull apart mechanism is something like this. So we have a depression like this, and this is SARS imagery. Red symbols, red color suggests, pink color suggests depression. And this is my photograph 6 weeks after the earthquake, and still I was able to find many water springs. So probably water plays some role. Matsushiro earthquake was triggered by water volcano coming up from the earth. Something may be related with this disaster. At the beginning of the study, we thought about undrained softening of very loose sand. This is shear stress effectiveness relationship, typical conceptual sketch. Dense sand behaves like this, but very loose sand suddenly collapses and effective stress decreases to 0. This is a well-known behavior of extremely loose sand under undrained conditions. But this possibility was declined finally because the collected undisturbed soil samples did not exhibit this behavior. So my idea is somehow the ground surface floated on water ejected by subsoil liquefaction, water film effects, or outburst of pressurized water aquifer, or ejection of tectonic water. Still, I have 3 ideas in my mind. I cannot decide on any one of them today. Sorry, I don't have time to discuss further about this, but this is without knowing the mechanism of ground failure. Still, I can calculate numerically, analytically, the distance of flow failures. Ground surface now floating above water, and the gravity force increases the stress in this direction. Beyond some point, this shear stress is compressional stress is greater than passive resistance, and passive failure happens. This is sort of mechanical idea. So consequences this riding over next pieces of soil. So this abduction creates shortening of the surface length. Originally, length was this much. After riding over, now distance along the slope surface is shorter than original length. So I integrated this shortening over the entire slope, and I was able to calculate the displacement, which reaches 700 meters, sometimes 1,400 meters in case of long slope. So somehow we can mathematically reproduce the long distance flow as happened in Sulawesi areas. But still we have questions about the mechanism of floating, how floating action happened during the earthquake. So now, okay, now time is up, I believe so. So summary, so nature is complicated. Yes, it's more complicated than human imagination. So 21st century will be the era of harsh natural environment, I mean global climate change, or more seismic action of the earth, and we have to encounter unknown types of disasters from now on. So we will have many jobs to do. Do you know who is this? Just want to say thank you very much for your attention. This is the end of my presentation. Thank you very much indeed. Okay.
Mark, we cannot hear you.
Mark, your sound is very funny.
All right. I think I'll take over. Thank you, Professor Towhata, for the very insightful talk. I think we have time for maybe one question from the floor. If you have any questions, can you please raise your hand or post your question in the chat window? All right. Then I have a question. Mark. Oh, I think it's not working. So I have a question, a quick question. You were talking about this very challenging scenarios, including the rain effect of rainfall. And in performing a numerical simulation, we are already using many assumptions in the simulation. So how should we address those challenging conditions in a numerical simulation? Do you have any suggestions or recommendations?
Yeah, thank you very much for these important questions. Yeah, as I said at the beginning, now we have problem of combined effects. Antecedent heavy rainfall may affect slope stability, instability during earthquakes. So in this sense, we have to think about more extreme conditions. Groundwater level, moisture content in slopes are higher than what you imagine under normal conditions. So, we should just use conservative input parameters such as groundwater table, etc. And we have to be prepared against this extreme conditions. Basic approach should be okay because you have computer cores, soil model, constitutive modeling. That's okay. I don't touch upon them. Just we have to use conservative input parameters. That's what we can do immediately. But on long-term basis, maybe we have to think about something else. But still, I don't have a good idea.
Okay. All right. Thank you for your response. I think now we are out of time. I would like to thank Professor Towhata again for the excellent lecture. And thank you everyone for joining the keynote lecture. Thank you.
Thank you. Thank you.